Welcome to Kitchen Table Electronics, Lesson 3.1, Python Basics. You've already uploaded Python 3 and the various packages, and you know where the idle IDE is. This rather long lesson is the grammar lesson that tells you what you need to know before we start coding for the class. You're going to try everything out in the Python shell in idle. You enter the commands at the 3 chevron prompt, and I do urge you to follow along with this, try things out, print out the presentation, and try all the bits yourself until you get on top of them. This lecture will be far too quick for you to follow and absorb everything first time around. So please play at the command console. You can do pretty much whatever you want to there, and please try messing up commands to see what happens. A couple of things that will help you out along the way. If you type help and then the name of whatever the object is on the screen that you want to know more about, it'll tell you about the object, and I called it whatever here. Control-C is another lifesaver. That will get you out of programs that stick somewhere without terminating. So, as I say, download the class notes and work through this, and then remember the reference I gave you at the beginning, which is the pythoncourse.eu set of tutorials. Be sure to look for help on Python 3. Just a quick hint here, when you see code online and you see statements like print x, you'll know that's Python 2. If you see statements like print open parenthesis x close parenthesis, then you'll know that's Python 3. I told you at the beginning that data types in Python are dynamically allocated according to context. Let's take a look at that. So here on the command shell, I've typed x equals input and then this string here, number question mark. What makes this a string are the quotation marks, and once I've completed them, idle made everything that was inside this string green, including the quotation marks. Input here is a function, it's made it purple, and then x equals assigns to x whatever this function returns. So if I hit return here, it prints this string out, number question mark. I typed in 1, I hit return, and it then will have assigned to x1. I then put another line in here, y, and the next number is, and hit return, and I put in 2. Then on the command shell, I typed x plus y, and I got, 12. Actually, I got 1, 2. Why is that? Because input from the keyboard is always assumed to be a string. And so this 1 wasn't the number 1, it actually was a string 1. And since you can't add strings together, the plus sign here then becomes the concatenation operator, and it says put string 1 and string 2 together, and so it puts out 1, 2. And the giveaway here is that the value returned by the shell has these parentheses around it, meaning I am a string. If I use a function here, this function integer, to convert the string to an integer, so I take integer of x plus integer of y and hit return, I get 3 as I originally expected. A little bit more on strings. We can define strings between single or double quotations. I'm a bit lazy about changing around, which probably isn't good. They're always colored green. We'll talk a little bit more on handling strings later, but I just want to mention that the use of 3 double quotation marks at the beginning and end of some text generates a special string called the docstring. Why might you want to have docstrings in your functions? Well, here's why. Let me show you the use of this help command. What I've done is imported a function here, sleep, that comes from this module time. I've used the keyword from, and notice how idle has colored it orange. So from time, import sleep, import another keyword. If I type sleep out, it tells me it's a built-in function. If I type help, this function here, open parenthesis, sleep, close parenthesis, it prints out the docstring, which tells me what sleep does. sleep ... sleep seconds delays the execution, this is of the program, not your execution, don't worry, for a given number of seconds. The argument may be a floating point number for sub-second precision. Aha, I didn't know that. I learned something right there. Floats and doubles. So if I want a float, it's quite easy. Instead of just typing x equals 1, which would assign x the integer 1, if I type 1.0, it now becomes a 32-bit float instead of a 16-bit integer. And Python just works this out from the decimal point. And so if I use the function type, I can see that when I put this in at the command shell, it returns it is a member of the class float, which is what I expected because I called it 1.0. What about doubles? These are 64-bit floating point numbers that have much higher precision. Well, they're not native to Python, but they are defined in this package Numpy, this numerical pi package. So if I import Numpy, I assign x to be an integer. So this is just a simple 16-bit integer. If I type x, it tells me it's 1, not point anything, because it's an integer. But if I now take y is numpy.double, so this function double of x, it will then return a double precision floating point number. And then when I put y in here, instead of being the integer 1, it's now the floating point variable 1.0. Numpy is an example of a class. A class is a collection of data and functions structured together in a particular way that let you get at it using some standardized commands. So once Numpy was imported, remember I imported Numpy, so it's sitting there in the Python shell, I can then just type numpy.double of x, and here we go, it produces the 1.0. When I extract a method like double from this class of functions Numpy, I create an instance of double as an object in my code. You can see what all the various bits are just by entering them at the command line. So numpy.double, it's a class numpy.float64 function, because that's what double is. If I just type numpy, you can see I get the complete path all the way back to where the package was installed when I used pip to put Numpy on the computer. Lists are another very important data type, and they are generated simply by using square brackets. So I am assigning to x the list 1, 2, 3, 4, 5, so the entries are just separated by commas. So if I put x now into the command shell and hit return, it returns the following list. Here's a really cool thing about Python. The list does not have to be numbers. So here I've made a list of strings. Python, notice the quotes, comma, is, quotes again, comma, fun. And then if I print out the elements of the list, which I can do by using the index to the list 0, starting at 0, 1, 2 for 3 elements, x of 0, Python, x of 1, hit return is, and x of 2, hit return fun. And once again, you'll notice that the Python shell has put quotation marks around these things because they are strings. All right, now let's make a 2D list or a matrix. Actually, this is not a symmetric matrix, but it's got 2 entries, each containing a list of 3 elements. I have here made a list, and then I have put the list within a second list that forms the second dimension of the matrix. To address this is very simple. Instead of using one index, so x of 0, I specify a second index, 1. So 0 here means the 0th list entered in the list of lists. That's this list here, that's the first list. And I want the number 1 element, so 0, 1, that's 2. So if I type this in at the command shell, hit return, back comes the number 2. Strings are also lists. They're lists, of course, of single characters, although Python doesn't use the character variable per se. And you can see if I define y to be this string that says a string, if I then type the 0th element, I get an s, the first element a t, the second element an r, and so on. So that's actually element 1, 2, and 3, but the index is 0, 1, 2. I can slice and dice elements of arrays, as you saw in that code I showed you before, where I said x plus y, and x plus y was strings, and they got to be concatenated. There is a whole host of slicing and dicing operations, appending, and so on, and you can look them up online. But you can do pretty much anything you want to do with arrays, merge them, and so on, and that can be very powerful. Another type of list you'll come across in Python, which I certainly hadn't heard of until I started to learn Python programming, was a tuple. At its simplest, a tuple is just an immutable list, meaning that it's a list of stuff that the program won't change. So here we are, I've defined a tuple, now without square brackets. So this means, computer, you can't change the elements in this list. And I put 99, 100, and wow, and then if I print my tuple of 1, you know that means the second element, and I get 100, my tuple of 2, and I get wow. You'll come across tuples because tuples are used for passing arguments into functions. When you go looking for help on Python functions, you'll often see as the arguments inside the parentheses that follow the function where arguments are passed, you'll see star args and star quargs. Args are the typical arguments that you might pass to a function. So if I wanted to add two numbers x and y, my function might be a function of x and y, and those would be star args, and I could specify them as being that type of argument if I wanted to. A quargs is a keyword argument, and I could specify something as being a keyword argument by using these two asterisks. I'm not going to do that, but you need to know it because when you go look at help files, you'll often see args and quargs and wonder what on earth they are. Another type of list in Python, tuple list, is a dictionary. This is a list in which the entries are paired. Now, notice to define a dictionary, I'm now using curly braces, and I now have, as each entry in the tuple, I have a pair of variables. So I've got the first, a pair of constants. I've got the first one, Stuart, and then a colon, and the second one associated with it. The next one, Alex, a colon, and the number associated with Alex, and so on. So if I now type birthdays at the keyboard and hit return, I get back this dictionary, all of it. If I use the get method, and so now I specified Christine, birthdays.get Christine, out comes, it looks for the element Christine, and outputs this number here. So a dictionary is exactly what it says it is. It's a lookup dictionary. All right, those are some definitions of types. Now let's get down to programming. The most important thing to tell you about is functions. So we will use functions all the time, and the format actually for almost anything in Python is the same. Keyword, in this case to define a function, def, and when I type that in, Python recognizes it as a keyword and makes it orange. Here's my function adding up, and then here are the arguments in this tuple here, x, y, and z, and then the colon at the end. So this tells me that this is defining the function adding up, and when I hit return, the next line is indented because the shell expects a series of commands that define adding up. So here are my commands. I'm assigning to the new variable result x plus y plus z, and then the new keyword here, return the value of this thing result. All right, so that has defined adding up. I had to hit return a couple of times because I had to get back to this side of the command shell. It's going to assume that every command you put in without getting out of these offset instructions is part of this function. So get out of the tab. If you have to, just push a back button to get back to this side here so you stop the definition of adding up. So if I now type adding up and I pass it the arguments 1, 2, and 3, I get 6 returned. Now, of course, testing things at the command shell is very powerful and very useful, and something I invariably do, particularly when I'm working with something that's new to me in Python. But you'll want to keep your functions when you've written them somewhere for further use. And to do that, you call up the text editor. You do that by using the file new from the shell, and up pops this text editor. This is what the window looks like. And in the text editor, in addition to defining your function, so here it is with all of the colors that you would get in the shell. So here's my adding up function. I can add other things. Because I'm going to save this, I will use a hash sign, which turns everything red. And so you can put a hash sign anyway. You can put it after these lines here. And that means that everything that follows on this line is a comment. And I very often use comments if I have something that is new to me or took me a while to work out. Just to remind myself what the problem was, I will put a comment next to it in the text editor. And being a text editor, it'll save the text comments. I also put a doc string in here, and you'll see why in just a minute. And then I saved it. And then if you go to the run button here, and then run module F5, you can use the F5 key. The module gets executed back in the Python shell. If you go look at idle, you'll see now you have two windows open, the text editor and the shell. So here's what happens when I press run in the text editor. It prints this out, and then it does absolutely nothing. Why? Well, we never actually called the function. We just defined it in that file, which was, by the way, called addingup.py. The extension .py was put on by the text editor. So now in the next line, let's type adding up 5, 6, 7. Hit return, and there we are. It executes to return 18. Notice that because I put a doc string in, even although this was our own homemade hokey function, it acts just like it does on everything else in Python and returns the doc string. All right, now we know about functions. Let's go to loops. Before I do that, I want to tell you about the list and range classes. Actually, I won't. I'll just tell you what happens if you type help list or help range. Out comes the doc string, and this, by the way, would spool down for pages, and if you read it, it tells you everything that list and range will do. List creates a list from the numbers generated by range, and so here we go. I have specified for range the arguments 2, which is the beginning of the range, and 10, which is the end of the range, and with no other arguments, it will now generate numbers 2, 3, 4, 5, 6, 7, 8, 9, and range tests to see that a number generated is always less than the top number, and so when you get to 10, it quits. So it doesn't generate 10. It generates the numbers 2 through 9. So range always does this, and then because I had a list here, it will print out on my screen. What I've done now is to add an additional parameter list to list, which is the step size, 2. So now it starts at 2, adds 2 to go to 4, adds 2 to go to 6, adds 2 to go to 8, adds 2 to go to 10, whoops, that's the end of the range, so it stops. And then, of course, because I use a list, it prints it out as a list. All right, now let's go to our loops. The important loop we'll use most of the time is a for loop. And here is the syntax you use of the for loop. For some variable, which I've called I, in another keyword, the range function, 2, 10, and then step 2, print I, and notice the colon and the tab offset here. All right, let's run that by hitting enough returns to get back here and run the function. And it prints out the list of numbers generated by range. Here's a really cool thing about Python. The list or the loop, for loop, will work with any list. So here I've made a list. I've assigned Monty to be this list here, string Python, comma, string is, comma, string fun. And then for I in Monty, colon, so this is my for loop, print I, offset by the tab, and then a couple of returns to get back to this side and run it. And sure enough, I equals Python, it prints Python. I equals is, it prints is. And I equals fun, it prints fun. Very powerful, and not a feature that's easy to program in other languages. Another type of loop is a while loop. And a while loop executes so long as a statement following the while loop is true. Statements to be true mean they are Boolean variables, often defined by setting, for example, x equals true. One will do as well, because the while keyword actually expects a Boolean variable here. So if I put 1 here, this 1 actually becomes a Boolean variable, which is 4 bits all set equal to 1. False would be 4 bits all set equal to 0, or I could use 0 here, once again assumed to be a Boolean variable because it follows a while. So this statement now actually has no way of being changed and will execute forever unless I do something to break this loop. One thing I can do is to actually put a Boolean variable here, which some other part of the program can change in order to stop the while loop. And that's something you may do quite frequently. Here what I've done, here's my program coming after this colon here. C is assigned to be input, enter a letter, and then I now break the loop, or allow for the possibility of breaking it, by now putting an if statement, a conditional statement. If C equals X. As you'll see in a second, the equals is really the equals in Python. The equals up here is the assignment operator. It assigns to C whatever the function input returns. But equals means if C equals X, in the English language sense of the word equals, then execute what follows this colon and is offset by a tab. And here I've used the break keyword to break out of the while. So here we are. I enter a bunch of letters, and when I enter X, boom, I get out of the function. Now, let's look at some more conditional control of loops, or anything else for that matter. The logical comparisons we can use are the equals, specified by 2 equals signs, not equals, specified by exclamation point equals, greater than, less than, greater than or equal to, less than or equal to. So those are all tests one can use, together with if, else if, and else. So let's look at this. While true, so this is going to execute forever. X equals input, enter a letter, that's my program. If X equals A, then offset again by a tab, print I always wanted A. Go back a tab to continue this while statement. Else if X equals B, and then colon and offset by a tab, not so keen on B. And then go back again, else if X equals C, then offset by a tab, statement to be executed. And then I go back here, else, meaning in all other cases, we do this, we break. All right, let's run that. So I enter A, I always wanted A. B, not so keen on B. C is okay. D, program ends. Okay, now let's deliberately screw up my while loop by deleting the else statement, else break. So now I have no way of getting out of this while loop. And sure enough, when I execute this without the else break, I enter a letter, fine, I always wanted A. Now I enter a long letter, nothing happens because there is no way of handling this particular case. So it just keeps asking me to enter a letter. And so in desperation, I use the Control C I told you about, and I get an error message here. I can avoid error messages like that. In fact, I can even include some quite detailed error reporting if I wanted, using the try and except keywords. So now what I've done is I've offset everything in this code over to the right by 1 tab. So I can put this whole block of code here inside a try and except block. So I try this, and it's going to keep working as long as these conditions are met here. But if these conditions are not met, it then does whatever the exception says to do, which in this case, print loop terminated with Control C. So when I do this, enter a letter, okay, I always wanted A, and then I put a Control C in, and it prints loop terminated with Control C. Now this is a little trivial because I could have put an else break in here, but I use this to show you that for more complicated error catching, for catching errors you probably haven't thought of, try and accept is the way to do it. What about taking data in and out from files? So to show you how file I/O works, I created a text file using Notepad called Python file test.txt, and all it had in was I typed in a single line, this is a text file to test Python file commands, and then we use the open function here, and the argument of the open function, the minimal argument, is just the path to the file. One thing, as a string, one thing that's really nice, by the way, is that once I've typed in C:\test data \, it automatically brought up a little block in the text editor, or actually in the shell, but it'll do it in either, which told me what files lived in that path. So I only had to click on the file to complete this, which was very nice, less typing. And then I've assigned that to an object now called file. And so if I type in file and hit return, this tells me what the object is. And then here is a program to read the file. For line in file, the file is an object which has a series of lines. I print this thing, line operated on by the method rstrip. The reason for this is that the end of the file has various characters to tell the computer in binary that we're going to the next line of the text file, and we don't want to try printing those out. The rstrip method just takes them out. And it's one of those things you have to look up online using the various resources. Here's a reference to file management. So if I run this, there's only one line in the file, and it runs and it prints out what was in the file, the text in the file, goes back to the command line, and here's an important thing, don't forget to close the file. And you do this with the close method, file.close, open and close parenthesis, hit return, and the file is closed. If you leave it open, other files on your computer will not be able to access it. Okay, we're nearly there. Let's talk about formatting strings when you print numbers out on a terminal or on paper or something. You can specify how you want the number to look, since you may be printing it into a table of numbers, so you can't have arbitrary digits scrolling all over the screen. The format specifier always looks like this. The first number here is the number of characters to be output. So including the decimal point, it's 6 in this example. 0.2 means that there are 2 digits to the right of the decimal, and then finally F means a floating point number. If you go online and look up string formatting, you will see tables of the various types of number you can format to output in a string. That includes things like binary, octal, and so on, as well as, of course, floats, doubles, integers, and what have you. The binary and octal and so on are actually quite important because we will, in this course, be accessing bits inside our Arduino, and we'll want to know what they look like. So we actually will use string formatting to get at that. But for right now, we're just going to format floating point numbers. How do you do this? Well, to do this, you include a special statement in your string where the variable is to be inserted, which consists of a left curly brace and a right curly brace. The first entry is a number that is an index to a tuple containing the arguments that are going to be put into the string. The second one is this format statement here. I've actually put 6.3f, but it's this format statement here. And then you use the .format method to pass the arguments as appropriate corresponding to this index in the string. I know that sounds a little tortuous, but it's actually quite easy, so let's use it. So first of all, I put in a definition of the number e. By the way, in Python, if you want a constant, you just write it this way. I could change the variable e if I wanted to, but if I don't, it becomes a constant of the program. So there is no actual constant variable in Python. And so here's e, here is pi, and then I have written the following print statement. Print e is colon, and then these curly braces here, which means print whatever the variable is with this format here, comma, pi is, and then the curly braces again, print whatever this variable corresponds to with this format, dot format. That's the format method being used right here. And the first index in the tuple there, which is 0, refers to the variable e, which actually happens to be that constant. And the second index, 1, refers to the variable pi. And then I need a final parenthesis to close off the print statement. By the way, if you miss it off, the command shell will just sit there waiting for you to put it in. And when you do, it'll execute it. So I put it in, I hit return, and I get e is 2.718, pi is 3.14. Notice here I have 1, 2, 3, 4, 5 digits with 3 to the right of the decimal point, and e was the first variable corresponding to index 0. Pi is 3.14, that's 4 characters with 2 to the right of the decimal point, as specified here. Now, if I switch these indices around, so now what I've done is I've put the index 1 here instead of 0, and the index 0 here instead of 1, and run the print statement, it tells me, quite erroneously of course, that e is 3.142, formatted to this 5.3f, and pi is 2.72, formatted to this 4.2f. All right, let's go to the text editor in idle, and let's use it to generate a program now instead of just defining a function. So here's the function we started with, this little function adding up, typed in as before and colored nicely by the program. However, I've now changed my doc string to say that this is a program called adding up 1. I put a number in there to distinguish it from the previous function. And so here's the doc string saying what it does. Here's my comment. And now I have an additional comment because this actually is the program that will use that function. And so here I go. I take the integer of the first number, integer value of the second number, integer value of the third number from the keyboard, and then I print the sum is, and then I call the function here that I defined up here, adding up of x, y, z. So now I've got a complete program, and I can then select run from the text editor and run the program in the shell. And when I do that, that's what I get. And I stop at this line, this enter x. I enter 1, I hit return. I enter 2, I hit return. I enter 3, I hit return. And then it calls the function adding up, and I get 6. Something else that the idle environment does is debugging. From the shell, this is actually the text editor here, but from the shell there is a debug option that you can toggle on and off. Before you do that, though, you need to set a breakpoint in the program, which is the point at which the program will stop executing until you use the debugger to step through it. To do that, you right-click on the line that you want the debugger to start at. So I right-click this line, and the text editor highlighted it in yellow. Now I go to the shell, and I select Debug and turn Debug on. Then I go back to the editor and click Run. And then up comes the debug panel. Here's the Python shell in the background. And what happened, of course, was it stopped at the very first enter statement, and I had to press step to step through the program. And I did it enough times till I got to enter X, and I pressed 1, enter Y, and I put in 2, enter Z, and I pressed 3. Now, when you do this, you'll discover that you are clicking the step button like crazy. Why is that? Well, it's because hidden behind all of these Python functions are an awful lot of code in the various functions that get called from the classes you use, even in a very simple program like this. So there are actually many hidden steps, and the debugger has the neat property of telling you what they are, but even in a short program, it gets very tedious. It has, of course, put out the values of the 3 variables I entered, which is good to know that it actually got what they were, and it tells you all about the variable types and functions up here. So a lot of information. It's actually too much information for me in general and too much hard work. I prefer to put print statements in to print out variables in the program that I want to know the value of to see if the program is working. Actually, I always do it with very small chunks of program. So if it's something that's completely new to me, I put it in the command shell and see if it works as I expect it to. Once I've got those tiny bits understood, I then put them in as small programs or functions in the editor and get them all working individually and save them as Python modules. And then finally, when I'm ready to put the whole thing together, I stitch the various components together in a Python file that contains the complete program. And that way I avoid the debugger. I suspect, getting very technical about Python, there are times when one will need it, but I found that to be the simplest way to making Python programs run and to finding errors. And by the way, the shell gives you lots of useful error messages. You haven't seen them because I have been careful to cut out the few places where I did not make mistakes in typing things into the Python shell. Okay, last topic just about. Using Windows, we are going to use Windows to open files, make plots and things like that. It's crazy not to do it on a modern computer with a GUI. Very simple to do in a simple way. tkinter is the toolkit that calls things from TK, which is a toolkit with widgets for various platforms, not just Windows. And so in Python 3, it's called little tk, and Python 2, big tkinter. So if I import it and then assign to root this object tkinter.tk, it actually opens a window on my computer. It opens one without this label up here. If I then execute the following widget, root.title, hello Pythons, the label appears up here on the top left. And finally, I'll want to get rid of this. Of course, I can click on the X, but if I've got several windows open and they can interact in some way, and I know I want to close one of them for good logical reasons, I then destroy this object here, root, which was set equal to this window, by this method here, root.destroy. So the Windows programming we're going to use is going to be, as I said, extremely simple, and I'm going to use examples taken from the internet that are very straightforward. I will make the following comment. Windows programming is different from the logical sequential stream that you think of when you write a computer program without Windows. The reason for this is Windows programs rely on actions. So they look for events like a mouse hovering over something, a mouse click, text being entered into a dialog box, and so on. So the main Windows program really consists of a bunch of event handlers that sit there saying, ooh, he or she just did this or that at their computer. I need to go and run some other code that will have been defined in a bunch of functions. It's actually, I find, very different programming Windows than from programming ordinary sequential programs. And I've given you an example of a program I wrote to teach myself GUI programming. And I should say that the approach I used was to take a photograph of the instrument that I was building a Windows interface for, so I could then lay out the windows to look like the instrument, define the logic that happened when you touched the various switches and read the various meters, and then built my Windows program around that logic. Quite different from how you write code to solve a fixed problem in one simple sequential screen without actions depending on Windows. And that, by the way, is in the advanced topics for this for this class, for this module 3 on Python. So finally, a few words about classes. We won't be writing our own classes, as Python already has something for everything, but you'll run into the guts of classes as you make errors in your programming or run into obscure difficulties with Windows functions. And you'll find that sometimes the methods and definitions come from somewhere you didn't expect them to, or put some code on your computer you didn't expect. So eventually you will become more familiar with classes. There is a very formal definition of how a class is structured. Obviously that must be the case in order to be able to extract functions from it easily, but you can read about it, and here's a reference to a tutorial on the python.org website. Another aspect is you might just want to be a stylish Python programmer, and probably my code to a proper Python programmer looks very ugly and very nasty. There is actually a style guide to make your programs pleasant to read and easy to understand by other Python programmers, and here's a reference for that. But with that, we have the tools we need to write the code we're going to need for this class. And so with that, let's go on to the next module in which we build our first useful programs.